Welcome to this next video in the playlist on field theory. In this video what we're going to talk about is algebraic field extensions. Okay, so we're going to start off with the definition of an algebraic element of a field extension. Then what we'll talk about is the definition of an algebraic field extension. Then we'll talk about the minimal polynomial for an algebraic element over a field F. Okay, so let's begin then with the definition of an algebraic element of a field extension. So let's let K be a field extension of F. So K is a larger field that contains F as a subfield. Okay, and let's let alpha be some arbitrary element of our larger field, capital K. So if I draw a picture for this, I'm not insisting that alpha is an element of the larger field extension outside of the smaller field. Okay, it could be in the smaller field, capital F. So let me just draw a picture for this. So here is my larger field, capital K, and here's my smaller field, capital F here. So we'll colour in the larger field, capital K, in red here, or rather we'll outline it in red, and we'll have the smaller field, capital F here, in orange. Okay, so alpha can be any element of the larger field, capital K. It could be in the smaller field, capital F, because after all, the smaller field, capital F, is a subfield of capital K, so all of the elements of capital F are in capital K, or it could be outside of F here. Okay, and for the sake of this picture, I'll just draw it outside of F, but it could be in F. Okay, right, so now the definition. Alpha is called algebraic over F, so we call this element of the larger field, capital K, algebraic over the smaller subfield, capital F, if there exists a non-zero polynomial which is in the ring of polynomials over the field, capital F, such that that polynomial has as a root alpha. Okay, so if there exists a polynomial which we'll call p of x, which is not the zero polynomial, so it's an element of the ring of polynomials over the field, capital F, except it cannot be the zero polynomial. Okay, so we take out the zero polynomial there, so it's not the additive identity of the ring of polynomials over the field F, so it's a non-zero polynomial in the ring of polynomials over F, such that if we apply the evaluation homomorphism at alpha to this polynomial, such that the evaluation homomorphism for alpha applied to this polynomial p of x, which would more normally be denoted p of alpha, okay, where you're just evaluating the polynomial at alpha, you get 0. Okay, so the evaluation homomorphism at alpha gives you 0 when applied to this non-zero polynomial. Okay, right. So firstly, let me just explain this evaluation homomorphism. So, of course, this polynomial, p of x, it's an element of the ring of polynomials over the field, capital F. So, of course, it's going to be also an element of the polynomial ring over the field, capital K. So, p of x here will also be an element of the ring of polynomials over the field, capital K, because, of course, all of its coefficients are from the field, capital F. All of the field, capital F, is contained within K, so it will certainly still be an element of the ring of polynomials over the field, capital K. And then we're viewing this evaluation homomorphism at alpha as being this evaluation homomorphism, which is a ring homomorphism from the ring of polynomials over the field K into the field K. Okay, and if you like, you can view this as being restricted down to the subring, which is the ring of polynomials over the field, capital F. Okay, and in a moment it will be helpful to view it in that sense, rather than thinking in terms of this huge ring homomorphism here. Okay, the point is that it makes sense to talk about the evaluation homomorphism for alpha acting on this polynomial p of x, which is in the ring of polynomials over the field, capital F. Okay, right, so that's the definition of an algebraic element. There must exist some non-zero polynomial in the ring of polynomials over the field, capital F, such that when that polynomial is evaluated at alpha, which makes sense by this evaluation homomorphism, you get 0 in the larger field, capital K, okay, which of course will also be 0 in the subfield, capital F. Okay, right, so that's the definition of an element being algebraic over F, and I want to stress that it's important to say that the element is algebraic over the smaller field F. Okay, it is important that you put on that over F bit. You can't just say that an element of a field extension is algebraic. It has to be clear that you're talking about some smaller field, because you'll note that this definition relies on you knowing about this smaller field. It relies on the polynomial being in the ring of polynomials over that smaller field. So we call this element algebraic over that smaller field F. Okay, right. Now, if an element is not algebraic over F, so there is no non-zero polynomial, which when that polynomial is evaluated at alpha gives you 0, so no polynomial in the ring of polynomials over the field which has that element as a root, then we call the element transcendental over F. Okay, so elements can either be algebraic over F or transcendental over F, and again, calling something transcendental, you must put the over F. It doesn't make sense to call something transcendental unless you are doing it with reference to some smaller field, in this case over F. Okay, so an element can either be algebraic over F or transcendental over F. Now the first thing to show you is that all the elements of the smaller field, capital F, are algebraic over F. Okay, so let's assume that alpha now is some element that's actually in the smaller field, capital F here, and let's show that it is algebraic over F. So just applying the definition, what we need to show is that there is some polynomial in the ring of polynomials over the smaller field, which is not a zero polynomial, such that when we evaluate that polynomial at alpha, we get 0. Okay, well this is very, very simple. Take the polynomial x plus the additive inverse of alpha. That is certainly a polynomial in the ring of polynomials over the field capital F, because the coefficient here in front of the x to the power of 1 term is just 1, and the coefficient here as the constant coefficient is just the additive inverse of alpha. If alpha is an element of the field capital F, then negative alpha will also be an element of the field capital F. Okay, so both of these coefficients are in the field capital F. Now when you evaluate this polynomial at alpha, you'll just stick in alpha for x here. The addition will now become addition in the field capital F, and you'll be adding alpha to its additive inverse, which will of course give you 0. So any polynomial in the actual, any element that's in the actual smaller field is always algebraic over that smaller field. The question becomes more interesting when we apply it to the elements that are in the larger field, capital K, but which are not in the smaller field, capital F. Okay, right. So there's the definition of an algebraic element and a transcendental element. Let me now give you the definition of an algebraic field extension. This is the definition of an element being algebraic over the smaller field, capital F. Let's now have a look at the definition of a whole field extension being algebraic over a field, F. Okay, right. So we will call the field extension K, which is a field extension over F, algebraic over F. So we'll call the actual field extension an algebraic field extension of F if it's the case that all of the elements in K are algebraic elements over F. So let me just write that down. So we'll call the field extension K, which is a field extension of F, algebraic field extension of F, if it's the case, so if for all, let's say, alpha, which is an element of the field extension K, it is true that alpha is algebraic over F, i.e. for all elements of the field extension K there must exist a non-zero polynomial in the ring of polynomials over the field capital F, such that when that polynomial is evaluated at this element alpha, you get 0. Okay, so alpha is a root of that polynomial. So that's the definition of a field extension being algebraic over the smaller field capital F. Okay, right, so those are the basic definitions. What I now want to look at is some theorems regarding algebraic elements of field extensions, okay, and what we can say about them. So the first and very, very important thing to talk about is minimal polynomials for an algebraic element alpha over a field capital F. Okay, right. So let's put this here. So this is an important theorem. Okay, so theorem number 1, if you like. So I'll just underline that in pink. Okay, right. So what we're going to say then is K is going to be some field extension of F. So K is a field extension of F. And now we're going to suppose that we have alpha, which is an element of our larger field capital K, which is algebraic over F. Okay, so alpha is algebraic over F. What I want to show, or even at first define, is the concept of a minimal polynomial for alpha over F. Okay, so alpha is algebraic over F. So what we know, just from the definition of alpha being algebraic over F, is that there must exist some polynomial which is a non-zero polynomial in the ring of polynomials over the field capital F, such that alpha is a root for that polynomial. Okay? What I am now going to claim, and here comes the actual theorem, so the claim of this theorem, okay, so claim that there exists a unique monic irreducible polynomial within the ring of polynomials over the field F, such that alpha is a root of that polynomial, and that polynomial is going to be called the minimal polynomial for alpha over F. So I'll write this down. So there exists a unique monic irreducible, so it's got a whole bunch of adjectives in front of it, a unique monic irreducible polynomial. Okay, so polynomial, I'll just put poly, in fact no, I'll put the full thing, polynomial, which we will call the minimal polynomial, and then we'll subscript it alpha, and then put a comma f, okay, of x. So both of these things are in the subscript here, so you should read this as the minimal, and I'll write out its full name. Okay, so the M is for minimal, okay, so it's the minimal polynomial, okay, for alpha, so that's why we've got the subscript alpha here, so for alpha, and then the comma is then over the field F. So you should, whenever you see this thing, you should read it as the minimal polynomial for alpha over F. Okay, and this is what we're going to define to be the unique monic irreducible polynomial, which is an element of the ring of polynomials over the field F. So that's what the over F bit here tells you, that it is actually a polynomial with coefficients in the field F. So it's an element of the ring of polynomials over the field F. So that's that bit. Okay, such that if you evaluate this polynomial at alpha, and I'll just now use the common notation, so M, the minimal polynomial for alpha over F, evaluated at alpha, you get 0. Okay, and this now is the bit, the reason that we have the for alpha here, so that's the alpha portion here. Okay, right, so let's understand this and see why it's going to be true, and then we'll have a look at why actually this is so important, and this is where we'll come back to the concepts that we saw in the previous video on this playlist on field theory entitled Field Extensions. Okay, right, so the claim here is that if alpha is algebraic over the field capital F, then there must exist a unique monic irreducible polynomial, which we'll call the minimal polynomial for alpha over F, which is an element of the ring of polynomials over the field F, such that this polynomial evaluated at alpha is going to give us 0. Okay, right, so the first thing to say is because alpha is algebraic over F, there must exist at least one non-zero polynomial in the ring of polynomials over the field capital F, which has alpha as a root. Okay, the instant you have one polynomial which has alpha as a root, you have a whole bunch of polynomials which has alpha as a root, because if you take any multiple of that, okay, if you multiply this polynomial, so going back to this definition up here of algebraic, if you then multiply the polynomial p of x, which is this polynomial which we're supposing is just some non-zero polynomial in the ring of polynomials over the field F that has alpha as a root, if you just multiply that by any other polynomial, q of x, and we'll assume q of x is not the zero polynomial so that you don't end up getting the zero polynomial as the answer, if you multiply it by any other polynomial except the zero polynomial, you'll get some other polynomial which will be non-zero now, okay, and that polynomial will also have alpha as a root. The reason being that the evaluation homomorphism is a ring homomorphism, so it obeys multiplicative compatibility. So this splits into the evaluation homomorphism applied to this new polynomial q of x times, in the field capital K, the evaluation homomorphism applied to the polynomial p of x. We know that the answer to this is equal to 0, so it really does not matter what the answer to this is, you'll get 0, because of course when you multiply any element by 0 in a ring, you always get 0 back again. Okay, so that means that this polynomial here, the answer to q of x times p of x, will also be a polynomial which has alpha as a root. Okay, so once you've got this polynomial p of x, which is a polynomial with alpha as a root, all the multiples of that are also going to have alpha as a root. Okay, right, so that's the first thing to say, that the instant element of this field extension K is algebraic over the smaller field capital F, we can say that there are going to be a whole bunch of polynomials in the ring of polynomials over that field capital F which have alpha as a root. Okay, so what we'd now like to do is show that in that entire great collection of polynomials which have alpha as a root, that there is only one polynomial which has alpha as a root which is monic and irreducible. Okay, and this will be the minimal polynomial for alpha over f. And there's actually another part to this claim. The other part to this claim is that if you have any other polynomial, so for all other polynomials p of x, which are in the ring of polynomials over the field capital F, and which have alpha as a root, so such that p of alpha is equal to 0, okay, and p of alpha is equal to 0 here, then this polynomial p of x will be a multiple of the minimal polynomial for alpha over f, so it will be something, shall we call it f of x, times the minimal polynomial here for alpha over f of x. Okay, so this is, if you like, part 2 of this claim. All other polynomials in the ring of polynomials over the field that have alpha as a root are just going to be multiples of the minimal polynomial for alpha over f. Okay, right, so I want to now understand why this theorem is true. So we'll start trying to prove part 1 here, and it's not difficult to prove at all. It's more that we just want to get an understanding for why this is true than we want to prove that it is true. Okay, right. So, this comes from the fact that the evaluation homomorphism is a homomorphism. Okay, so let's think about this evaluation homomorphism. And we know that the evaluation homomorphism at alpha, our algebraic element, can be thought of as going from the domain ring as the ring of polynomials over the field F. So remember back up here, I said, okay, initially you would think about having this evaluation homomorphism going from the ring of polynomials over the field extension capital K into the field extension capital K, but let's very quickly reduce our attention down to this sub-ring of the ring of polynomials over the field extension K, which is the ring of polynomials over the field capital F. Okay, this is just a restriction of this basically, so it's still going to obey additive compatibility, multiplicative compatibility, and the fact that the multiplicative identity will go on to the multiplicative identity over here. Okay, so it's still going to be a ring homomorphism, and that's the one that's going to be more useful for us to consider down here. Okay, so we've got this evaluation homomorphism at alpha, which is taking all of these polynomials in the field capital F, okay, so where the coefficients are from capital F, and it's taking them onto some element in the field extension capital K by evaluating them at alpha. Now, because this is a ring homomorphism, the kernel of this must be some ideal within here. Okay, so we're going to consider the kernel of this ring homomorphism. And why are we so interested in the kernel of this ring homomorphism? Well, the kernel of this ring homomorphism is going to be all of the polynomials which are mapped onto the additive identity here. Okay, and all of those polynomials which are mapped onto the additive identity by the evaluation homomorphism are going to be all of the polynomials which have alpha as a root. Okay, so all of the polynomials with alpha as a root are the kernel of this homomorphism. Okay, this evaluation homomorphism. Now, here comes the clever bit. We know that this is a we know that this ring of polynomials over the field F is a Euclidean domain. Okay, and all Euclidean domains are principal ideal domains. Okay, so we know that the kernel of this ring homomorphism must be some principal ideal generated by some polynomial. Okay, so it must be the principal ideal generated by some polynomial. Okay, and what should I call that polynomial? Okay, I'll just make something up, so we'll call it a of x initially. Okay, so it's generated by some polynomial a of x. Okay, now let's just think about this a little bit more, because I claim that this is actually going to be generated by our minimal polynomial for alpha over f. Okay, but I want to explain that more rather than just writing it down in front of you. Okay, so let's think about what all of the things in this principal ideal generated by a of x are going to look like. So they're all going to be multiples of a of x. Okay, so they're going to be things of this form, q of x times a of x, where q of x is some element of the ring of polynomials over the field capital F. Okay, now, there's one strange one here, which is where you multiply it by the zero polynomial. When you multiply it by the zero polynomial, of course, you get the zero polynomial. So one of the elements that you can always say is going to be in this ideal is going to be the zero polynomial. But for all other q of x's, okay, so for q of x is a constant polynomial or a non-constant polynomial, anything but the zero polynomial, this product q of x times a of x is always going to have degree greater than or equal to the degree of a of x. Okay, so it will just go up and up and up. Okay, so the one exception is when you multiply it by the zero polynomial and get the zero polynomial back again. For all the other products, you have something of degree greater than or equal to a of x. Okay, that means that the polynomial which generates this principal ideal has the smallest possible degree, okay, of any polynomial in this principal ideal, okay, because remember we don't bother defining the degree of the zero polynomial, okay, so it will indeed have the smallest degree of all the polynomials in here. Now, what you can do is modify this polynomial a bit. You can change it so that it is monic. This polynomial I've used here might not necessarily be monic. Okay, so a of x might look like this arbitrarily. It might be a0 plus a1 x plus all the way up to an x to the n, i.e. its leading coefficient might not be 1. Okay, however, what you can do is you can multiply it by the multiplicative inverse of an here. Okay, so you can always multiply it by this constant polynomial, 1 over an here, and then of course what you will end up with will be monic. So these coefficients will all change, but this one will change to 1. Okay, so you'll end up now with a monic polynomial. So we've now got a monic polynomial of minimal degree, and I claim that that one of course will be in this principal ideal generated by a of x, because it is just a multiple of a of x. But I also claim that we can use that polynomial to actually generate this principal ideal. Okay, so if you use that instead, this will generate the exact same principal ideal as here, because this is just an associate of this one. This is a unit in the principal ideal generated by the field capital F. Sorry, this is a unit in the ring of polynomials over the field capital F. Okay, so this polynomial that we've got here, this is just an associate of this one. So indeed, this polynomial will be in the principal ideal generated by a of x, and also this polynomial a of x will be in the principal ideal here, because I can just multiply this back by an here to get this one. So because they're both in each other's principal ideals, the two principal ideals are equal to one another. I hope that's fairly obvious that this one will generate the same principal ideal as this one. Okay, so you might as well assume that the polynomial that we've got here of least possible degree is a monic polynomial, because you can always find a polynomial in this ideal of a least possible degree that is monic. Okay, and this polynomial I claim is going to be your minimal polynomial for alpha over f. Okay? Right, so what I need to prove now is that that is the only monic irreducible polynomial in this principal ideal, in this kernel of this homomorphism, i.e. it's the only monic irreducible polynomial which has alpha as a root. Okay, so that's how I'm going to find the minimal polynomial for alpha over f, by looking at the kernel of this homomorphism and finding a monic polynomial of least degree that generates the kernel when you take its principal ideal. And what I now need to prove is that this does indeed satisfy the condition that it's the only monic irreducible polynomial in this kernel, okay? Right, so it is indeed monic. We need to prove that it's the only monic irreducible polynomial, okay? So, the first thing to say is that it cannot be irreducible. It cannot be reducible, and the reason it cannot be reducible is that if it was reducible, it would be writable as two things that are strictly smaller than it. Okay, so if it was reducible, we could write it as, what should I call these? B of x times c of x, where neither of these were units. And remember, in the ring of polynomials over a field, units are constant polynomials and non-constant polynomials are not units. So these will have to be non-constant polynomials, i.e. they'll both have to have degrees strictly less than this one. Okay, then if you apply the evaluation homomorphism to both sides of this, you'd get, obviously, the evaluation homomorphism applied to the minimal polynomial would give you 0. And then on the other side, you get the evaluation homomorphism applied to b of x times the evaluation homomorphism applied to c of x. Okay, and then we'd have two things multiplying together in the field capital K to give us 0. That would imply that one of these had to be equal to 0. Okay, so it would imply that one of these polynomials, b of x or c of x, was in the kernel of this ring homomorphism, this evaluation homomorphism at alpha, and that would contradict this being the smallest degree polynomial in this kernel. Okay, so that's why this has to be irreducible. It cannot be reducible, otherwise you wouldn't have successfully found the smallest polynomial in this kernel of the ring homomorphism, which does have to exist. It is true that that has to exist. There must be some polynomial with the smallest degree, and that's one of the polynomials that you can use to generate the kernel by taking its principal ideal. Okay, so this is irreducible, okay, so are all of its associates, so are all the other polynomials in this kernel which have the same degree as it, so all of the constant polynomials times this, all of the associates of this, such as a of x initially was, that was an associate of this, that was just an times this, okay, that will also be irreducible because it's just an associate of the minimal polynomial of alpha over f. However, it will not be monic, so we're still, at the moment, it looks as though we are going strong to have a unique monic irreducible polynomial in the kernel of this ring homomorphism. Then all we have to consider is all of the other polynomials in here, okay, not the ones that have the same degree as it. Well, firstly, the zero polynomial. The zero polynomial isn't irreducible. You can't apply the definition of reducible and irreducible to the zero polynomial because it's the additive identity. Reducible and irreducible only apply to non-zero, non-unit elements of the ring. Okay, and then finally, the polynomials that have degree greater than the minimal polynomial of alpha over f. Okay, they're just going to be multiples of the minimal polynomial of alpha over f. Okay, so they're going to be in the principal ideal generated by this, so they're going to be some other polynomial, q of x, times the minimal polynomial of alpha over f, and this other polynomial that you'll have multiplied with them will not be a constant polynomial because they have degree greater than this. So if you just multiplied it by a constant polynomial, of course the degree wouldn't go up. So you're going to have to therefore have all other polynomials written as a non-unit element times a non-unit element. Okay, and therefore they are reducible, they're not irreducible. So all the other polynomials in the kernel here of higher degree than the minimal polynomial of alpha over f fail the irreducible portion. The polynomials of the same degree as it fail the monic portion, and the zero polynomial that just fails the irreducible portion as well, and the monic portion. Okay, so indeed this is the only polynomial in the kernel of this homomorphism that is monic and irreducible. Okay, so we have proven that there is a unique monic irreducible polynomial in the ring of polynomials over the field f, which has alpha as a root, and we will call that the minimal polynomial for alpha over f. And indeed, this is the polynomial which generates the kernel of the evaluation homomorphism when you take its principal ideal, and therefore all the other polynomials in this kernel are just multiples of this. Okay, so this portion becomes obvious as well. Okay, right, so one more comment that I want to make, which is really, really important now. Okay, so if we then consider producing the field generated by alpha over f, okay, so remember this is something that we define in the video on field extensions. This is the smallest subfield of the field capital K that contains this element alpha. Okay, so what we're imagining doing now, okay, here is our larger field capital K, here is our small field capital F, and we're imagining now, because otherwise it's just not interesting, that alpha is an element outside of F. Okay, it's not something that's inside of F, it's something that's outside of F here. Okay, so here's our smaller field F, here's our larger field K in red there. Okay, now we've got some algebraic elements. We're supposing alpha is algebraic over F. Okay, so I'll just add that onto the picture here. So it's algebraic over F. Okay, and we're now considering generating the field through alpha of F over F. So we're considering generating a field extension of F, which is the smallest subfield of the larger field capital K, which completely contains F and completely contains alpha. So if you like, on this picture, it could be something like this. Okay, so I'll colour it in green there. So this could represent our field generated by alpha over F. So it's a subfield of the larger field capital K, and it's the smallest subfield that completely contains F, and it also contains that element alpha. Okay, now, because we know alpha is algebraic over F, we now know that there will exist some minimal polynomial of alpha over F. Okay, so alpha will have a minimal polynomial of alpha over F, which will be some element of the ring of polynomials over the field F. Now, from the previous video, we know that the field generated by alpha over F will be isomorphic to a construction that we spent so long exploring in the previous video on field extensions. We know that the field generated by alpha over F is going to be isomorphic to the ring of polynomials over the field F, quotiented out by a polynomial which is irreducible in the ring of polynomials over the field F, and which has alpha as a root. This is such a polynomial. This is the unique irreducible polynomial which has alpha as a root in here and which is monic. Okay, you could use any of the associates here as well, but why would you? We might as well use this minimal polynomial. So we can quotient out by the minimal polynomial of alpha over F here, the principal ideal generated by that. Okay, so we're just now putting in place here from the previous video, where we've now gone is we've gone from just putting a p of x here, which was that polynomial which was irreducible in the ring of polynomials over the field F and which had alpha as a root, and now we're using this terminology, the minimal polynomial for alpha over F, okay, which is such an irreducible polynomial in the ring of polynomials over the field capital F, which has alpha as a root. Okay, right. As I say, you could use any of its associates as well, but you wouldn't want to use any of the higher degree polynomials in that principal ideal, which is the kernel of the evaluation homomorphism at alpha, because those wouldn't be irreducible, so it wouldn't apply for those. So you do need to use an irreducible polynomial. We might as well use the monic polynomial, which is this minimal polynomial here. Okay, right. So what I would like to now do is give you more intuition for what this is actually saying than I successfully gave you in the previous video. Okay, but before we just do that, let me just make one more little definition. Okay, so another definition regarding algebraic elements over a field capital F is the degree of an algebraic element. Okay, so you can define what's known as the degree of an algebraic element over the field capital F, and you just define this to be the degree of the monic polynomial of alpha over F. Okay, that's perfectly sensible. This polynomial will have some degree, okay, so you can indeed define that. Now, why is that an interesting thing to do? Well, because what is the degree then of the field generated by alpha over F going to actually be? Well, it's going to be the degree of this quotient ring over F, and we know from the previous video that the degree of this quotient ring over F is just the degree of the polynomial that you're using to generate the principal ideal by which you're quotienting out by. Okay, so this would actually end up being the degree of the field generated by alpha over F here. Okay, right. So that's why that is a very nice thing to define the degree of an algebraic element to be, because it's the value that you'd get as the degree of the field extension if you generated the smallest subfield of the larger field capital K, which contains F and this algebraic element alpha. Okay, right, so that's just another little comment to make, but now let's go back to the really important bit, the understanding of this isomorphism, because, as I say, we showed this isomorphism in the previous video on field extensions. What I now want to do is give you some real intuition as to what this actually means and why this is so important. Okay, right, so I'm just going to remind you firstly of the isomorphism that we actually had from here to here, because that's going to be really important for me to be able to explain what this means. And where we're heading is I will be able to now give you a description of how to construct this thing, the field generated by alpha over F, which at the moment is still quite a abstract idea. We don't have much intuition for what this is, but by saying it's isomorphic to this, we can get a huge amount of intuition for what this thing is. Okay, so let me point out the isomorphism that I showed you in the previous video on field extensions. Okay, so the isomorphism we called zeta in that video, and it was a mapping from this quotient ring, the ring of polynomials over the field F, quotiented out by the principal ideal generated by the minimal polynomial of alpha over F, like so, okay, into the field generated by alpha over F here. Okay, now how did this work? Let me just remind you how this worked. Well, it came from the evaluation homomorphism for alpha, okay, acting on the ring of polynomials over the field F. So the way we defined this is it would take any coset that contained a polynomial, so the coset that contained the polynomial a of x here, and it would take it onto what any representative in this coset was mapped onto by the evaluation homomorphism at alpha. Okay, so we could take the representative a of x and then just take the evaluation homomorphism at alpha for that polynomial a of x, and that would be an element in here. Okay, so let me just draw a picture to show you this. So firstly, let's put on the evaluation homomorphism at alpha. So we've talked about the evaluation homomorphism at alpha already in this video. What I'm now going to do is change the codomain field from being the entire field capital K just to being the field generated by alpha over F, because all of the answers that I get from doing this will be in the field generated by alpha over F, okay, because all we're doing is taking alpha and taking it to certain powers, multiplying those powers by elements of the field capital F, and then adding them together, okay, so all of those operations are going to end up giving us answers that are in the field generated by alpha over F, so we might as well restrict our attention down from the entire field capital K just to the field generated by alpha over F. Okay, so here I'm drawing out the evaluation homomorphism at alpha firstly. So here's the field generated by alpha over F. Okay, this is going to be initially the ring of polynomials over the field capital F, so we'll have this in purple or pink here, the ring of polynomials generated by the field F here. And then of course what we're going to have is the evaluation homomorphism. So I'll firstly put the evaluation homomorphism here. So here is our evaluation homomorphism that just takes any polynomial in here and evaluates it at alpha, gets some answer over here. Now, what of course we did is we quotiented out the ring of polynomials over the field F by the principal ideal generated by the minimal polynomial of alpha over F. Okay, so what we'll do is we'll get, let this be the principal ideal generated by the minimal polynomial of alpha over F here, like so. So I'll just colour that in, so we'll have this shown in orange here, like so. And then of course what we've done is we've formed the additive cosets of that. So we've partitioned our ring of polynomials over the field capital F into the additive cosets here. And then the way that we've defined this mapping is that we map each of the cosets here, which are our elements in the quotient ring, onto the element which all of the representatives in each coset are mapped onto over here. Okay, and remember in the previous video we show that all of the elements in the same coset, the same additive coset of the principal ideal generated by the minimal polynomial are going to be mapped onto the same element in the field generated by alpha over f by the evaluation homomorphism. And just to give you the intuition of why that's true, if we consider all of the elements in the minimal, the principal ideal generated by the minimal polynomial of alpha over f, they are all going to be mapped onto a single element over here. They're going to be mapped onto 0. Okay, effectively what we're doing is we're just applying the first isomorphism theorem of rings here, because we're just taking our initial evaluation homomorphism from the ring of polynomials over the field capital F to the field generated by alpha over f now. Okay, and we're saying, okay, this will be isomorphic now to the quotient ring. Okay, that's what we're really doing here. But just to say that again, the elements of the principal ideal generated by the minimal polynomial, all of those are going to be mapped onto 0 by the evaluation homomorphism at alpha, so they're all going to go onto 0. And in fact, all of the polynomials that are in the same additive coset of this principal ideal generated by the minimal polynomial of alpha over f are going to be going onto the same element under the evaluation homomorphism. Okay, so they're all going to be mapped onto the same element over here by the evaluation homomorphism. So that allows us to very sensibly define where each of these cosets is going to go onto here. It's just where all of the elements in the coset are actually going to be mapped by the evaluation homomorphism. So that's how zeta works. It just maps each of the cosets onto where the evaluation homomorphism would map all of the elements in that coset. So just take a representative from the coset, ask what the evaluation homomorphism would send that element onto, and that will be the answer as to where zeta would send the coset. Okay, right, and so the intuition then behind this, what does this really mean? Well, it allows you to understand completely how to build this field generated by alpha over f. So going back to our original problem, you've got the field capital F, you've got the element alpha here, okay, and you want to generate the smallest subfield of the larger field capital K, which contains f and alpha. You want to generate the field over f, which contains alpha. Okay, how do you do this? Well, basically, what you have to do is you have to look at all of the polynomials in the ring of polynomials over the field capital F, and you have to evaluate all of them at alpha. Okay? You will get answers that are in the field capital K. So you go through every single polynomial in here, you evaluate them all at alpha, you get loads of answers that are in the field K. Loads of the polynomials will give you the same answer. So for instance, all of those in the principal ideal generated by the minimal polynomial of alpha over f will give you the same answer. They'll all give you 0, but loads of them will give you different answers as well. You collect all of those answers together into a set, and that subset is going to be the smallest field generated by alpha over f, the smallest field that contains f and alpha and is a subfield of the larger field capital K. That's how you construct this thing, and that's what this is telling us basically. Okay, and the reason that it is telling us that is, look, that's exactly what we've got effectively here. Okay, all of the polynomials in these cosets, in these additive cosets of the principal ideal generated by the minimal polynomial of alpha over f, all of them are being sent onto the same element in the field capital K. Now remember, this is just a subportion of the field capital K. Okay, but they're all being sent onto an element in the field capital K. Okay, and they're all being sent onto the same element. So that's what we're really doing here. This is just dividing up the ring of polynomials over the field F into these sets of polynomials that are all going to be sent onto the same answer in the field capital K when they're actually evaluated at alpha. Okay, so these are the sets of polynomials that when you actually do this, when you actually evaluate them at alpha, will give you the same answer. They won't give you a different answer to add into your subset that you're trying to build here. Okay, and I'm now saying that this is beautifully in correspondence with the elements that will be in the field generated by alpha over f. Okay, so that's why I can say that if you actually do this, if you actually just evaluate all of these polynomials over the field f at this element alpha that you're trying to get included in here, okay, and take all the answers, I know that that will be a subfield of the field capital K, and the reason is that, look, it's in isomorphic correspondence with this structure that we've generated here, which we know is a field extension of the field capital F. Okay, and that's how I can conclude that indeed this subset here is going to be a subfield of capital K, because it's in isomorphic correspondence with a structure that I know is a field. Okay, so I hope that's clear. What I'm telling you here is how to construct this thing. I'm telling you that if you want to construct the field generated by alpha over f, which previously we didn't really understand that well, now we know exactly how to construct it. Just evaluate all of the polynomials over the field capital F at this element alpha, collect together all of the answers you get. Of course you will get the entire field capital F because of all the constant polynomials here, which will just be mapped onto themselves. Okay, collect together all of those answers, and that, I claim, that subset of the field capital K will be a subfield, and it will be the smallest subfield that contains alpha and F, and you can think for yourself why it will be the smallest subfield. Okay, you can't have a smaller one because you have to have all of these polynomials evaluated at alpha. Okay, I hope that's fairly clear. Okay, and we know that it will indeed be a subfield because of the fact that we have established this isomorphic correspondence here with another structure that we already know is a field. Okay, so because this is in isomorphic correspondence with something that is a field, we know that that must also be a field structure. Okay, right, and that's why we can conclude that if we do this, if we just evaluate all of these polynomials over the field capital F at alpha, the subset that we get, the subset that we collect together, that will actually be a subfield of the larger field capital K. Okay, so I know I've emphasized that hugely, but that is such an important concept to get across. Okay, so I hope that you do now understand that. We'll have a break here, and in the next video we'll look at further theorems regarding algebraic field extensions.